Good day everyone. In today's lecture, we'll be discussing about the two transistor analogy of an SCR, how we can get the operation of an SCR using two back-to-back connected transistors, that is an NPN transistor and a PNP transistor. And in the next half of this lecture, we'll be discussing about various turn-on methods of an SCR.
SCR is a four-layered three-terminal device. It has three terminals: anode, cathode and gate. Anode is connected to the upper P layer, cathode is connected to the lower N layer, and gate is connected to the inside P layer. Now we know that we are discussing about the two transistor analogy. In two transistor analogy, we get the operation, we can understand the operation of a thyristor by using two transistors, that is an NPN and a PNP transistor. Now from the construction of an SCR, what I will do is the inner two layers I'll split it into two and I'll make it into two devices, that is a PNP transistor Q1 and an NPN transistor Q2. So here I am having two transistors, that is if I connect these two transistors back to back, I'll get the operation of an SCR. Now to understand that, let us look into this figure. Now in this figure we can see that the upper portion, the upper PNP is becoming one transistor Q1, the lower NPN, that is after cutting my SCR into two halves, I am getting two transistors. One is an NPN transistor and one is a PNP transistor. The upper, that is the upper portion of the PNP transistor is having anode and my gate. The lower transistor, it has the cathode. Now as we all know that a transistor has three terminals: emitter, collector and base. So we will look into the circuit diagram of this arrangement. Now this is the circuit diagram of the arrangement. Now here we can see that this is the upper PNP transistor, this is the lower NPN transistor. Both the transistors are connected back to back. Here we can see that the emitter of transistor 1 is equal to anode current. Then we can see that the base of transistor 1 is equal to the collector of transistor 2. This is my second transistor's collector and first transistor's base, both are the same thing. Then here one more thing I can see, that is the collector of the first transistor and the base of the second transistor are the same thing. Then the second transistor's emitter is equal to my cathode, IE1 is equal to my cathode. Now from this I can understand that the first transistor's emitter is equal to my anode current. That is, if this was an SCR, then the current that is entering here would have been called as a anode current. As this is a PNP transistor, the first emitter's current is equal to my anode current. Then the second emitter's current, it is called as my cathode current. If this whole arrangement was an SCR, here the current that is coming out, I would have called it as the cathode current. Now this is a transistor. As this is a transistor, the second transistor's emitter current is called as my cathode current. Now here also I have alpha 1 and beta 1, these are the current gains of the first transistor. Alpha 2 and beta 2, these are the current gains of the second transistor. So from this diagram it is quite clear that the base and collector both are interconnected. Of both the transistors, the base and collector both are interconnected. Now let us move on to the derivation part. Now we look into the modeling of two transistor analogies derivation. Now we know that the common base current gain is equal to IC by IE. This is a common understanding that we have. Now what I will do is I can write this to be IC is equal to alpha I. I am just cross multiplying it. So this is the portion that I am getting. Now other than this, a small leakage current will also be present, that is called as ICBO. ICBO is nothing but the leakage or the common base leakage current. So this is my base that I am going to keep, and based on this I am going to write equations for my transistor Q1 and for my transistor Q2. Now what I will do is I will just substitute the substitute I'll just modify the equation. This is my base equation. Now from this base equation I have IC. If I'm talking about my transistor 1, this will become IC1. Then I have alpha IE, this will become IE1. As we have already discussed, IE1 is nothing but my IA. So this is becoming alpha 1 IA. Then I have ICBO. ICBO is nothing but the leakage for the first transistor. That is why I am getting ICBO1. Now writing for the second transistor. In the second transistor, the collector current, it will become IC2, alpha 2. IE is nothing but it is IE2. IE2 is, as we have discussed, IE2 is nothing but IK, and we have ICBO2. ICBO is nothing but the leakage of the common base leakage current of the second transistor. Now based on this, I am getting two equations, equation 1 and equation 2. Now what I will do is, I can clearly understand that, let us look into this diagram. I can clearly understand that the incoming current is IA. Now before reaching this portion, I can see that this, if I am considering this to be the outgoing, I can see that IC1 and IC2 are outgoing. That is IK, whatever IK I will be getting, it is because of IC1 and because of IC2. Or I can write because of IB1 and IB2 as well. That is, incoming current is IA. That is, IA is the amount of current that I am passing, and this IA is flowing through IC1 and IC2, and I am getting IK. So I can write this to be IA is equal to IC1 plus IC2. Now already I have derived what is the value of IC1 and IC2. Now what I will do is, I will just substitute those values. This I am just adding it here. This I am writing it to be here. I am adding both the quantities. After adding both the quantities, I am getting a new equation, and that new equation I am turning it to be equation. I am naming it to be equation number 3. Now if it was an SCR, if it was an SCR, what would have happened? Whatever current, that is IA current and IG current, both would have get added, and I would have get cathode. Whatever current that I am receiving here is because of whatever current is going through these 2 points. So I could write IK is equal to IA plus IG. Now let us check here. Now I have written here to that IK is equal to IA plus IG. So in this equation, wherever IK is there, I will substitute the value IA and IG. Why I am doing this? I am doing this because in my first equation is in terms of IA, and second equation is in terms of IK. So I cannot find out any common elements. I have to find out some common elements. So for that purpose, I will be substituting the value of IK in equation number 3. After substituting the values, alpha to IK, it becomes alpha to IA IG. Now what I am doing is, I am removing some common elements. So after removing common elements, I am getting the value of IA to be alpha to IG plus ICBO1 plus ICBO2 1 minus alpha 1 plus alpha 2. The value of alpha 1 to alpha 2 will always be should approximately be equal to unity, or it should near unity, the value of alpha 1 and alpha 2. This I can know that ICBO1 and ICBO2 are leakage currents. Its values in some cases we will be neglecting that because the leakage currents value will be very low value, or it will be in the terms of milliamperes. So this is the final expression that I am getting for two transistor analogy of an SCR. Now moving further, we will discuss about the various turn on methods of a thyristor. Now basically speaking, for turning on a thyristor, we have 5 commonly used methods, that is forward voltage triggering, gate triggering, dV by dt triggering, temperature triggering and light triggering. We'll look into each of the methods in detail. Now let us move on to the first method. The first method is called as forward voltage triggering. So as we have already seen in the modes of operation of an SCR, we had 3 modes of operation. The first was reverse blocking mode, the second was forward blocking mode, and the third was forward conduction mode. Now when we were discussing about forward blocking mode, we have seen that the VAK is forward biased, or the voltage that I am applying across my anode and cathode is forward biased, but to the gate I am not giving any signals I am giving, or the gate is not connected. Now in this case, when I am increasing the VAK or the forward bias voltage, when I am increasing, at that time there is a avalanche breakdown, and because of this avalanche breakdown, or it is the avalanche breakdown, I am getting to a point called as VBO, or the forward breakover voltage. When I am reaching the forward breakover voltage, an avalanche breakdown will occur, and because of this avalanche breakdown, my SCR will start conduction. So here I am not giving any gate, but only what I am doing, I am increasing the anode cathode forward biased voltage, and because of that increase, my SCR is turning on. So this is my first method, that is called as my forward voltage triggering. Then, as I was discussing, the third mode of operation was forward conduction mode. Now in forward conduction mode, the VAK that I had applied was my forward bias, and also I had applied a positive gate current I had applied. Now based on this positive gate current that I have applied, we have seen in the graph, let me take you back. We have seen in the graph that is depending on what forward voltage, what forward gate current I am applying, I can easily quickly turn on my SCR. Now this was the breakover voltage that I was talking about. Now breakover voltage, when it is reaching, I get forward conduction, and because of gate current that I am applying, I get my second mode of operation, that is called as gate triggering. So in gate triggering, VAK, the voltage across anode and cathode, will be forward biased, and also to my gate I'll be giving a gate current I'll be giving, and this gate triggering is the most commonly used method for turning on a thyristor. In any device that we take, most commonly preferred method will be gate triggering. Then we have the third type of triggering, that is called as dV by dt triggering. dV by dt is nothing but the rate of change of voltage. Now for example, my voltage is increasing, my voltage has to increase 10 volt, it is increasing 10 volt in 10 seconds. Now this is a let us see what will happen in dV by dt. It will increase for 10 volt in 1 second. Now here we can see that the time period taken is very low, that is here the rate of change of voltage is very high, that is in 1 second 10 volt increase is there. Here in 10 second there is 10 volt increase, so here the rate of change of voltage is less. Now we know that there are three junctions in my SCR, J1, J2 and J3. J1 and J3 are forward bias, but J2 is reverse bias. Now because of this depletion layer, it will act like a capacitance. Now across this capacitance, we can say that IC, the current that is flowing across the capacitance, is equal to dQ by dt. We know that Q is nothing but C by V. So here CG, I am denoting it to be CG because it is the capacitance of the junction. Now when I am derivating that, I get IC is equal to C dVA by dt plus VA dCG by dt. I will be getting this term, I will be getting. Now the rate of change of capacitance, there is no term like that. So dC by dt, its value is constant, therefore its value will always be equal to 0. So I'll get the remaining term, that is IC is equal to CG dVA by dt. Now if the rate of change of voltage is more, if the rate of change of voltage is more, it plays a very important role in turning on the device. Now because dVA by dt value is increasing, because of that the current in the junction or the capacitive element that is forming across the SCR, it will substantially increase. Why? Because the rate of change of voltage is high. As this is high, this will also tend to be high, and because of this I will be getting dV by dt triggering. So this is called as the third type of triggering. And the fourth type of triggering is temperature triggering. In temperature triggering, when the temperature is increasing, as we all know that for freeing the electrons, either if I'm giving an external energy, I'm giving temperature, the heat energy, if I'm giving temperature when it is increasing, when the temperature is increasing, because of the increase in temperature, there will be increase in leakage current. That is, because of the increase in temperature, some electrons and holes will be freed. Now there will be an increase in the leakage current. Now as some electrons and holes are freed, the depletion layer that is formed across junction J2, the depletion layer formed across junction J2, there will be a reduction in the width of this depletion layer. As there is reduction in the width of this depletion layer, now when there is a reduction in the width of this depletion layer, some amount of current will start flowing, and because of that, as the temperature is increased, there is an increase in the production of holes and electrons, and because of that, the width of the depletion layer is decreased. As the width of this depletion layer is decreased, we can see that by increasing the temperature as well, I can turn on my SCR. And the fifth method is called as light triggering. In light triggering, we can see that the light is made to enter the inner P layer, or in place of gate, what I'll use is I'll have a small cutting in my P layer, and because of this, the light will enter here. Now the photons that are present in light, they will generate some free charge carriers, and because of those free charge carriers, it is like giving a gate current. It is like giving a gate current. Why? Because some free charge carriers are generated, and because of this, what will happen? The width of depletion layer will reduce, and because of that, my SCR will turn on. Now these are the 5 methods that are commonly used for turning on a thyristor, that is forward voltage triggering, gate triggering, dV by dt triggering, temperature triggering, and light triggering. If